next speaker is Professor Vijay Kumar Chikadi. I have already introduced him once. I'll do it again. So he's from ISAR Pune, and he will be telling us about identifying structural defects that govern the relaxation in amorphous solving.
Thanks, Shantan. First of all, I would like to thank the organizers for this invitation and this opportunity to present this work to you. So let me start with introducing myself. Many of you are we are meeting for the first time. My name is Vijay Chikadi, and I'm an experimentalist. We are at Indian Institute of Science for Education and Research in Pune. That's where we are. So the movie that you're seeing here is actually data taken from experiments. So what is being done here is this is a dense colloidal suspension, and we are shearing the suspension. Okay, as we shear, we see that there is plastic deformation in this in the colloidal glass, and what you're seeing here is just how this plastic deformation occurs or propagates as you strain the system. And this is what I'm going to talk about. The title of the talk is Structural Origin of Relaxation. I'm not only going to talk about sheared systems, but also quiescent systems. So what we're looking at is the relaxation in these systems and how do they connect to, is there a structural origin to the relaxation? So this is what I'm going to talk about. The work that I'm going to present today is mainly the work of a PhD student, Ratima Nasi. And most of these ideas that I'm going to present today are based on the theory that was provided by Sarika and a student. So they are in NCL, and we have a long-standing collaboration with Peter Shah. So these are the people who were involved in this work. And let me start with this slide. It only tells us that the mechanics of solid has a very long history. It goes back to the times of Da Vinci and then Galileo. If you look at the manuscript, they try to understand how these different kinds of material respond to applied stresses. Okay, so they made in some of their manuscript, they made these kind of drawings. You can see here the beams. How do they bend in response to applied load? Okay, so this was probably they were trying to understand architecture or in the context of constructing structures. These were important. And also, once again, in the manuscript of Galileo, you can see that he had these thought experiments how to estimate the strength of a pillar column or even a rope like this. Okay, so this is this slide is also to cheer myself that in the age of quantum information, there are several questions that are still unanswered. We take them for granted. These are essentially things, you apply stress and the material breaks, deforms. We take it for granted without realizing the beautiful physics that is underlying these processes or these phenomena. And I tell my students again and again that even though we are in quantum information age, there are several beautiful problems in physics that are not understood, and this is one of those problems. And I'm going to tell you a little bit about what we have discovered about these things in our experiments. So the experiment is very simple. The problem is very simple. You take an elastic solid, you apply stress. We are looking at disordered solid. You apply stress on this, and this is the kind of macroscopic response that you see in the system. On the y-axis is the shear stress, on the x-axis is the strain. For very small strains, there is a linear increase in stress with the strain. So that is and then Newton, and then after a certain strain, there is nonlinearity. Nonlinearity sets into the system, and there's a yield point beyond which a material either flows like a liquid or it breaks down if it is very brittle. Okay, so this is generic, and this is a behavior that you see in a variety of materials. And there's no need to emphasize why we are studying these problems. This is a fracture community. I don't have to really explain. There are these catastrophic failures which we want to understand them in a better way. So our approach is, this is more of a macroscopic picture. Our approach is to understand this problem from a microscopic perspective. What happens on a particle scale? Starting from there, how does deformation propagate to macroscopic length scales? And so why disordered systems? I mean, if you look around us, there are a lot of materials that can be classified as disordered rather than ordered materials, okay? And once again, it's a big umbrella of material. You can see that there are a variety of materials that can be classified as amorphous solids, and the length scale ranges from nanometer to centimeter scale. So this is a big umbrella, and then the hope is that by studying one of these systems, we can understand how the other materials also deform. So that's the motivation for us. So even before I start talking about disordered systems, let's take a moment to look at how ordered systems, ordered solids deform. So our ordered solids are generally made of these defects, and when you apply stress on them, this is what happens. So the movie that is being shown here were the experiments that were conducted by Bragg and Nye and Bragg and his collaborator way back in 1950s. What you're seeing here is this is a bubble wrap, which is created on a air-water interface. You just put bubbles and then compress them, go to high densities. They form these crystalline rafts, okay? And then these crystalline rafts show many of these defects that you find even in atomic systems. And deforming these kind of systems and then seeing how deformation occurs on a particle scale is very easy. So as you deform the boundaries, you can see that there are defects that move like quasi-particles, so from one boundary to the other boundary. So this is dislocation picture. Now we would like to ask whether one can extend this picture of defect motion and dislocation motion to amorphous system, and it's going to be difficult because in ordered systems you have a regular lattice with respect to which one can identify the defects, okay? But in the case of amorphous system, there is no underlying lattice. So the question is how do we extend this notion of defects to glasses? Are there defects? I mean, can we identify defects in these systems by looking at the structure is the question that we want to answer. So the two main questions that I'm going to delve upon is what are analogs of defects in glasses, and how does it, is there a correlation between structure and then plasticity in these systems? So so what I'll do in the next few slides is I'll take you through some of these ideas that have been developed over the years, trying to understand how deformation occurs in these glassy systems. And one of the earliest idea that came about in this area, disordered systems, is based on this free volume proposed by Franz Papen. And again, this model was motivated by Turnbull and Cohen. They were trying to develop a theory for glasses based on free volume model. And this is once again they extended those ideas to understand how deformation occurs in disordered systems. And once again, when you talk about disordered system, as I said, the configuration is amorphous. There could be certain regions that are loosely packed, and there could be regions that are tightly packed. Okay, so it's a very intuitive picture, intuitive model. So when you apply stresses, probably you can imagine that there are certain regions that are loosely packed, and those are the ones that are going to fail. Okay, so and when you say loosely packed, once again, this idea of free volume, it comes naturally as the agent to a structural measure to look at. And what he said was essentially this atom is going to move under, if you apply stress, this particle is going to move only if there is sufficient volume, if there is sufficient volume available to it. Otherwise it will not move. And then based on that, they develop this kind of model. This is the strain rate, how the deformation rate occurs based on these parameters, okay? And essentially, this model takes into account the free volume available in the system, and based on that, it predicts what is going to be the shear rate if you apply a certain strain rate on the system. And now, this was the first set of ideas, and then, these ideas were taken forward by Bulatov and Augen. They made, certain modifications to this model. What they said was that, if you have a local deformation, if a particle is moving from one, if a certain neighborhood is getting deformed, then the attempt rate, for those local inelastic transformations is given by this, this is based on the transition rate theory. One can write the rate of these transformations in this fashion, and delta is just the free energy. So delta G is the free energy barrier that one has to surmount to see these rearrangements in the system. And this delta G is essentially when you apply stress on the system, it is getting lowered because of the applied stress in the forward direction. Okay, so that is what it says. Like, so when you have an applied stress on the system, they can, the free energy the energy barriers get lowered, and then there will be more rearrangement. That is what this equation essentially says. And one of the important elements that he introduced here is that he brought in this idea of elastic deformation. So whenever you have a rearrangement, you are storing elastic energy, and this will get dissipated in a certain way. Okay, so this is the energy gets dissipated. The stress has to get redistributed, like whenever there is a flip, and that has a long range nature. Okay, the stress relaxation. So essentially, what he said was that, let's say you have a volume 1, and then there is a strain a volume element omega 1, and then you are applying a strain epsilon EIJ on that element, and it's going to deform in this to this shape like omega 2 with a stress sigma ij, and then he showed that one can relate this sigma ij, the stress that is developed in this, based on this equation. And we don't have to get into the details of that. What it essentially says is that the stress decays it has a long range character. Okay, so that's the key point here. One can write down this nice elasticity equations and then show what is the green tensor that is relevant in this equation, and it has a long range nature. And for certain geometries, you can show that what is done here is you have a spherical inclusion that is strain, and then you're looking at the far field strain decay, and this has a quadrupolar structure. Okay, so this is once again the solution corresponding to linear elasticity equations derived by Eshelby. Okay, so this was one of the important additions they made to this contribution they made to this problem, Argon and Bulatov. And now, these ideas became very popular. So, in the recent years, there have been a lot of MD simulations on plasticity of amorphous solids. And this is this is a strain, stress, and then strain curve that you notice in a simulation, in MD simulations. And what you see here is, these are all quasi-static deformation simulations and done at temperature 0. What you see here is that it's not a smooth line like the one that I showed earlier. So there are a lot of serrations along this. There's a rise in the stress, but these are punctuated by a lot of these serrations. Okay, so what happens is you apply stress on the system. There is a elastic loading, and then suddenly there is a plastic drop because of which the stress decreases. And then once again there's whenever the stress drops, there is redistribution of the stress. And then once again there is elastic loading. So this way the system the plastic deformation or the deformation in the system proceeds in this fashion. So elastic increase, and then a plastic drop, elastic increase, plastic drop. So whenever you have this plastic drop, when you are in this transient regime, when the strain very small before the system has attained a steady state, if you look at what happens when one can, these are all MD simulations, 0 temperature, you can write the Hessian for this, and then diagonalize, find out the eigenmodes, and you look at the lowest eigenmode that goes to 0, and then if you look at the structure of the eigenmode, it has this kind of a structure. What you're seeing here is the displacement vectors. Okay, so whenever there is a plastic drop, you can see the lowest the structure of the lowest frequency in the system, and then this has a quadrupolar structure. This is what you see when you look at the displacements. Now, this is at small strains. However, when you go to steady state, it's not just one isolated event. You have multiple events occurring at whenever there is a plastic drop, and there is essentially a cascade of drops in the steady state. So these are the characteristics of plastic deformation that were discovered in this paper. There was a lot of focus on this, but then this particular paper brought all these things very clearly. So, I'm just taking you through how deformation occurs and what has been done so far, and then what we're going to do further. Okay. So once again, all these were simulations, and now there were some experiments done using colloidal glasses. These are dense colloidal suspension. You can do shear measurements and then look at the local level, particle level strain. Okay. So Yeah, so I mean, if you want to do these kind of things in atomistic systems, experimental systems, it's going to be very difficult because we need to resolve the motion of single particle. But in colloidal suspension, these particles are larger. We can use microscopy to visualize, like, what is the local strain field in these materials. And then what they showed was that essentially, like, you have this kind of a cortical structure whenever there is a shear transformation occurring. So for example, what is happening in these two steps is you're looking at this zone, and then you see that this is at strain gamma 1, and then this is at strain gamma 2. As you strain, like, further, what you see is that there is a red, like, high strain event occurring here, and then it is associated with this cortical structure, okay? So which was also predicted by Eshelby's which is also predicted by Eshelby's solution. So these were some of the first observations on the characteristic of water plasticity carriers in these systems. So once again, later on, like, we use this kind of a correlation function, strain correlation function. A here is the shear strain. I mean, one can compute the strain tensor based on you take a particle and then look at the relative displacement of this particle with respect to the neighbors. And then one can extract a strain tensor from this displacement information, and then one can plot different components of the strain. What is plotted here is the shear strain component, and then epsilon is the correlation of the shear strain. This is the xz plane. So epsilon xz, what is being plotted here is correlations of epsilon xz. And then if you look at these correlation functions, once again, you see this nice cortical symmetry. What it says is that essentially all these shear transformations are the zones that have high strains, that those correspond to something like Eshelby's inclusion in this material. So that's what it says essentially. So you have like a high strain, and then like the surrounding material, like the surrounding matrix has elastic character. So because of this transformation, it has this kind of cortical strain decay. So that's what it says.
See similar structure in that normal components as well, like in the strain.
They have different symmetries. So yeah. So based on the symmetry, like we see we have done actually compared to experiments and simulations. I mean, we get similar results. Whatever like response you see in simulations, I mean, we can see the same response in experiments too.
Okay. Yeah. But those are different from this one, because here only the correlation is between shear.
Yeah, exactly. Yep. So now these were like some of the ideas. What we learn from these from this thing is how does plasticity occur like in these systems. Essentially, like you don't have dislocations. There are like group of particles within the system that locally like deform or change their neighbors. Okay, so there is localized deformation in the system. So all these red zones, like they show like local deformation in the system. That's how like the disordered system is going to deform when you apply stresses on them. Like there are in the case of the crystals, like you have these dislocations that travel from one point to the other. But in this case, like there are the dislocations are these shear transformations. Okay, that's how like they are the plasticity carriers. That's how plastic deformation arises in these systems. Now the second question is what we have done so far is like we have characterized like how does deformation occur in these systems, and what is the characteristic of these plasticity carriers. Now the second question that we want to answer is if there is a shear transformation here, we call these high strain zones as shear transformations because they are the ones that are carrying plasticity. So if I see a shear transformation here, like the second question is like why does it form in this particular zone? Is there something special about this zone structurally that the plastic event occurs here? So that's the question that I'm going to answer. How is the structure related to local plasticity? That is the question that we want to answer. And before I answer that question, I would like to take you through some of these ideas that were proposed very recently. So structure, like I introduced the first structural measure that I introduced was free volume. And there have been a lot of experiments, colloidal experiments and simulations. They have not found a strong signature between these shear transformations and local free volume. Okay, so naturally, like that made us look for other structural measures to correlate the structure to plasticity. And this was one of the ideas that was proposed in the context of relaxation of glasses. Okay, there is no stress. The rearrangements or the relaxation is occurring due to thermal fluctuations. So the idea here is that once again, they wanted to capture the structural aspects. Where do these rearrangements occur in the system due to thermal fluctuations? Okay. And to characterize the structure, they use this kind of they used this kind of structure functions. So this is G, it characterizes. So there is this Rij sitting here, it characterizes the structure as a function of distance from a tag particle, and then there is this Psi, which takes into account the angles between the particles. Okay, so essentially, there is information about radial distance, and then there is also information about the angles in these structure functions. And then what Andrea Liu and our co-workers did was that they fed a lot of simulations data to this machine learning techniques, and then made the technique learn how way the deformations or the particle rearrangements occur. And then based on that, they predicted how they predicted something called they calculated something called softness field. Okay. Based on the structure functions, they calculated a softness field. The softness field tells you the regions in the material where the rearrangements can occur very easily. Okay, so that is what is the softness. Essentially, you can think if a region is soft, that's more susceptible to rearrangements. Okay, so that's the kind of quantity they came up with. It's a structural measure based on these structure functions. And now what they did was they computed two things. One is PR is rearrangement probability based on the softness. Okay, you can calculate the softness for each and every particle based on these two structure functions, and you can associate a softness value to a particle and then see whether as a function of this softness, how does the rearrangement probability depend on this softness. Okay, and then what is plotted here is once again what you see here is that as the softness increases, the rearrangement probability increases. What it means is that softer a particle, the larger is the probability for that particle to rearrange. So so this was a very nice structural measure using which they could characterize this rearrangement probability very nicely. And then once again, here what you see is that the delta E, the energy required, the energy that you need to surmount to see a rearrangement as a function of the softness. So as the softness increased, the energy barrier that you need to surmount to see a rearrangement was going down. Okay, so this was a very nice result. However, this was all based on machine learning techniques. And if you start thinking about what this softness parameter is, what is it motivated, what is it capturing, trying to give a physical meaning to this softness parameter gets a little difficult. Okay, so since these structure functions are dependent on essentially particle coordinates, so okay, fine. So let me present this before I go further. So once again, these ideas found support even in experimental systems. These are experiments done by Rajesh and his co-workers. And what they saw was that they initially started with amorphous configuration. They characterized based on the structure of the particles. They characterized the local softness of each and every particle. And the pink, the background that you see here is the softness field. And on top of that, what they are showing is if you start with an amorphous configuration, you let the system relax. What happens is after very long time scale, several relaxation times, you will see that the system crystallizes. Okay, and then these crystallization, the crystallites, the particles that form crystalline configurations, they appear in these zones where the particles were softer. Okay, so you have a reference configuration with respect to which you calculate the softness, and then you look at the system. You wait for several hours, maybe 100 hours. That's the kind of time scale that they have waited here. And after that, you see what is the configuration of the system where the particles have formed crystalline patches, where the crystalline patches are formed in the system, and they essentially appear up on these regions where the particles are soft. So so they were there was a lot of this idea was very popular. So now the question was, as I said, all this is the softness function is calculated based on the structure. Okay, essentially all that you need to know is where the particles are sitting. So what Sarika and her co-workers did was they came up with a microscopic theory for softness. Okay, so now they developed a new softness measure They called it softness, but it's not the same machine learned softness. I'll tell you a little bit more about what this softness is based on a macroscopic theory. And they were essentially able to see the same results that they found in machine learning things. So what it says is that now we have a softness measure, that is derived from a macroscopic theory, and then you can understand it well, appreciate it well, you know what you're computing. Okay, unlike in machine learning techniques where it becomes very tricky to associate meaning to what is being computed. So this is what I'm going to talk about. So these are simulations, and then we have done some experiments based on these ideas. I'll tell you what these ideas are, and we have used colloidal suspensions to validate some of their ideas in experiments. So we have done experiments under shear and also under rearrangement due to thermal fluctuations. Okay, so these are the kind of systems. I'm going to skip this part so that if you have any questions, you can ask me. These are just colloidal suspension, 1 micron particles, and then they are Brownian. You can see at very high densities, all that they do is they jiggle around their mean position. So they are baked, and then they contain fluorescent dye. We can see these particles in 3D. Okay, so not only on a single layer, but you can see in 3 dimensions how these particles move. So this is the kind of system that we have. 7%. Yeah. We don't have a right number because maybe I'll tell you later. Sometimes, but you see that if you look at this configuration, you don't see too many crystalline patches. So yeah, it's not you don't see too many crystalline patches in the system.
Okay. Yeah. Thank you.
We just mix 2 batches of particles and then some are suppressed.
It's a biodispersed mixture.
It's not a biodispersed mixture. It has
size distribution. Yeah. So that's the natural polydispersity of a PMM.
Exactly. Cisdeclin and CHP. Yeah, so this is the kind of system that we have, for sharing the system, the bottom boundary is kept constant and the top boundary is moved with a constant velocity. We are applying shear rates, constant shear rate in the system, and the shear rates are in this. This is the magnitude of the shear rates that we're using in the system, and we are tracking large number of particles, close to 250,000 particles. And this is the kind of system that we have. We can, as we shear the system, we can see, we can record the images of the particles and then see, how they're moving in 3 dimensions. If you look at a typical particle, how does it move? On some small time scales, you see that it's jiggling around a mean position, and if you allow sufficient time, it will escape and then go to a nearby cage and then, do this kind of motion. Okay. So once again, one can extract a relaxation time scale from that thermal motion. So that turns out to be 20,000, and then this is the applied shear rates are in this are of this values, and then one can estimate what is a modified Peclet number. This is just the product of these 2 time scales, gamma dot and then the time scale, and the Peclet number turns out to be 1, which is weakly driven. These are not strongly driven systems. So these are the kind of system that we are looking at, and if you look at the shear rates that we are working at, and what is being plotted here is the displacement of the particles. This is the kind of geometry that we have. One of the plate is being moved and the other plate is stationary. This is a plane shear. And if you look at the displacements of the particles as a function of distance between the boundaries, you see that there is a linear displacement profile. There are no shear bands in the system. It's a homogeneous flow. So now, what we want to do is, we want to relate the rearrangements in our system to the structure. So the way we do it is, I'll not present all the details, but tell you, the important points, so that we understand, the idea that is involved here. So you take n body system, and then, what you can do is, using mean field approximation, you can say that within the mean field approximation, you can look at a single particle, the fluctuations of single particle, and then you are essentially freezing the surrounding particles and then coming up with an effective potential that a particle feels due to the presence of the rest of the particle. That is the mean field assumption. Okay, so you can start with this is this goes back to that Fokker-Planck equation, BBG by hierarchy kind of thing. You have evolution equation for each and every particle, and then you can reduce it to a single particle with an effective potential. So that is the idea that is being used here. So you take any type particle, it sees you can make mean field approximations, and then say that this experiences a caging potential because of a frozen background. So that is a kind of a picture that is presented here, and this is based on mean field approximation. And now what is the what is this potential? So that's what we want to understand. Okay, so based on mean field potential, we come up with these mean field ideas. We come up with this idea. Now the next thing is what is this effective potential that a particle is feeling? And we go back to these ideas of Ramakrishnan and Yusuf, and they proposed an expression for the effective potential based on liquid state theory ideas. And I'll just show you what this expression is. So this is the expression for the effective potential that a particle feels, and C of Q is the direct correlation function. S of Q is the structure factor. C of Q is dependent on S of Q. So essentially, if you know the structure factor, which is essentially all you need to know is the structure in the system. So if you know the structure in the system, then one can derive what is effective potential in the system. And what is being shown here is that effective potential. Okay, based on this information, the structure factor, one can derive what is effective potential in the system as a function of density of colloidal particles. Okay, so you can see nicely that when the density is low, the effective potential is shallow, and as you make the density higher and higher, the colloidal density, the effective potential becomes deeper and deeper. Okay, so one can use this kind of expression, you make a harmonic approximation. You say that your effective potential has this form, harmonic form, and essentially the curvature of the potential is the structure factor, the structural order parameter. Okay, so this is inverse of the stiffness of the potential. Okay, so what we are essentially deriving from here is the stiffness of the potential. We are taking an inverse of that, and we are calling that as our structural order parameter. Okay, so this S, which is the structural order parameter, this is essentially the inverse of the curvature of the caging potential. If you look at this as a function of phi, you will see that as you increase the density in the system, the structural order parameter, what it tells us is that the susceptibility to a rearrangement, how soft or how hard the local neighborhood is. Okay, this is not on local neighborhood. This is averaged over all the entire system. Okay, so what is the stiffness of this effective potential is what it is saying. You are taking an inverse of that. So you are essentially looking at 1 over the stiffness, so which is essentially softness. Okay, so let me use the word softness so that it is easy to understand. So we are looking at 1 over the stiffness, inverse of the stiffness, which is the softness. So S is essentially the softness, but this is not based on the machine learning technique, but this is based on the caging potential. Okay, the softness is derived from the caging potential, and one can show that one can extract the curvature and also the depth of the potential. You can see that they essentially they are linearly dependent on each other. So what we say is that instead of looking at the curvature, one can look at the depth of the potential. Okay, so the inverse of the depth of the potential is going to be your structural order parameter. Okay, so essentially whatever information is there in the curvature, it's also there in the depth of the potential because of this linearity. So now this is the whole idea. Okay, so now what one can do is this is based on Q space. Okay, which is you're taking into account the entire system. Now we want to extend these ideas can be extended to a local particle level. Okay, so defining S of Q on a local level is going to be hard. So what we do is we go to real space, and then we can show that the depth of the potential is essentially given by C of R and G of R. G of R is the pair correlation function in the system, and the C of R is related to the pair correlation function in this fashion. Okay, so now what we can do is based on G of R, we can find out what is the stiffness or the inverse of the stiffness, which is the softness for our system on a particle level. Okay, so since G of R can be evaluated on a particle level, we can also compute what is the softness on a particle level. So if you look at this GFR is essentially modified, otherwise if you look at the bare GFR, it has a lot of fluctuations, and what we do is we do modification using this kind of a function, and you see that depending on this sigma, you get you do modification at different levels, and then you optimize the sigma so that you you retain some of that some of those local density fluctuations, okay? And that's how we come up with the optimal value of sigma, and that's the sigma that we use in our experiments. And so what we do was that, like now using this formulation, what we can, based on the structure of the particles, coordinates of the particles, we can compute what is the local caging potential, what is the local stiffness, or the inverse of the stiffness, which is the softness, okay? So first, what we thought was like, let's apply these ideas to crystals. I mean, there is nowhere in this formalism it says that it's applicable only for amorphous systems. It is equally applicable to ordered systems also. So first thing what we did was we took a defective crystal, and then we a conventional way of identifying defects in this system is based on this bond order parameter. Okay, you look at how you connect neighboring particles using bonds, and then you look at how these bonds are oriented. Based on that, you can identify the defects in the system, and this is a conventional way of doing things. And what it essentially says is it gives you information about the geometry, nothing else. Okay. So now we do we calculate the structural order parameter for the system, and then it also captures all these defects very nicely. Now what is interesting about this is the structural order parameter, or the softness that we calculate in our system, gives us information about the local softness, okay, local caging potential. So that is much more it's giving you much more physical insight into what these defects are. The other the bond orientation, it just gives you information about geometry. Okay, so it works very well for crystalline system, and we can also do this for a 3D system, and you can see that it captures very well these grain boundaries in 3D systems also. So that was very nice. And what we do here is we take a colloidal monolayer, a binary mixture of colloidal monolayer. So it's not a 3D system, it's a monolayer, but it's bidisperse. We kill crystallization by taking bidisperse system. And this is at a density of 73%. And what we have done is we have essentially calculated the local level softness or the structure order parameter for this for these guys. And you can see that there are regions that are hard, there are regions that are soft. And to characterize this in a better way, what we do is we can look at the distributions of the structure order parameter or the softness in our system. And what we see here is, once again, as you increase the density, the curve shifts to lower softness or lower structure order parameter. What it says is that as you increase the density in the system, the overall softness of the system is getting lower. It's lowering. Okay, so that's why the distribution is moving in this fashion. One can look at the average of these things, and then you see that as you increase the density in the system, the softness or the structure order parameter in the system also decreases. Okay, so now what we have done is we really wanted to understand, now that we have particle level information, we wanted to check, we had this idea, so if you have rearrangements in the system, if you have amorphous configuration, there could be certain regions that are soft, there are certain regions that are hard based on the local configuration, the local neighborhood, okay? So just to check that, what we have done is we picked all the soft particles in the system, and we grouped all the soft particles and then all the hard particles in the system, and then we looked at the local GFR for hard guys and then the soft guys. It's an averaged plot, for all these particles, and then you look at GFR for the particles that have a larger structure order parameter, or some with the particles that are soft, and then particles that are hard. You can see that the hard particles are associated with a more structured environment. Okay, so this goes by, this confirms our intuitive understanding of the disordered systems. There are certain regions where the packing is loose, and then there are certain regions where the particles are tightly packed. So in those regions, the hardness, the system should be hard, and then particles where the regions where the particles are loosely packed, it should be associated with higher softness. Okay, and that's what it confirms. Okay. So now, with decreasing softness, we also see that the relaxation time in the system also shoots up. So let me go to the next thing. So,
okay. So see, I just wanted to ask you, so these are very, very dense suspensions, right? So we know from Wilson Poon's very famous paper that, the systematic errors can easily be 3%, 3 to 6% in measuring the, the volume fractions of very dense suspensions. So I just wanted to comment, I mean, can you put an error bar on these concentrations that you have, the densities that you showed us in the last figure? I saw 70
Yeah,
and
so this is something.
73.
Yeah, this is something that we can do. Yes, yes.
No, but I just wanted to ask you. So, I mean, what are the error bars
So
of the
we haven't
density?
looked at the error bars, but I mean, what we see here is, there is a a trend, with changing area fraction that gives us a little confidence. But of course, we can go back and then put error bars on them and see what's happening. But this trend, I mean, is something that is seen in experiments, simulations.
No, I just wanted to know how you.
No, sure. We can do that.
No, what is the experimental protocol in calculating the density of the suspension?
So the density of the suspension. So using images, you can.
So you're counting particles.
Yes, we're counting the particles, and then the manufacturer, we have the radius or the size of these particles from manufacturers.
So you're not really considering the nonlinear effects at these very high volume fractions. Okay, thank you.
Yeah, so now so far I've spoken about how to characterize the structure in the system. So next part is how to correlate the structure to the rearrangements in the system. So the rearrangements can occur for two different reasons, either due to thermal fluctuations or due to applied shear in the system. So first, what we're going to take a look at is the rearrangements that occur due to thermal fluctuations in the system. And what I'm showing here is how do we identify rearrangements in our system, and that is based on the cage relative displacement. Okay, I've not given the expression for delta CR. So essentially, you have a particle and you have the neighbors. You look at the displacement of this particle with respect to the neighbors, okay, the first nearest neighbors. They are identified using the first minima in GFR. So you identify the first nearest neighbors, and then you calculate the cage relative displacement of the particles, and that's what is plotted here as a function of time. And at small time scales, you see that there is this caged motion. This is at the dilute 60%. Okay, this is not 60.6, I would say. So this is the dilute, the most dilute solution, the most dilute system that we have in our system. And yeah, there is a small subdiffusive regime. And then if you wait for a longer time, there is once again a slope of 1 that is coming here. So there is a crossover from subdiffusive to diffusive regime. So we take this crossover point as the characteristic time scale in our system, and then this is the characteristic displacement in our system. Okay. So on this time scale, if a particle has a displacement that's greater than this, then we call it as a rearrangement. So that's how we identify rearrangements in our system. And the first thing that I'm going to show here you is the distribution. This is P of S, the distribution of the softness. And then this is the distribution of the softness of the particles that are rearranging over a certain time scale. Okay, over a time scale, this is those notations are missing. This is tau r. Okay, and then this is some displacement scale. This gives us the displacement scale. This gives us the time scale. So on this time scale, we are looking at the rearrangements, and then we are plotting the distribution of the structure order parameter or the softness for those particles, and you see that their softness is larger. Okay, so if you take the mean of this curve, okay, for all the particles, and then you draw a line, and then in the red curve, there are 90% of the particles in the red curve have softness greater than the bulk softness or the average softness in the system. So what it means is that essentially the rearranging particles have higher softness or are associated with a higher order parameter, higher structural order parameter. So now, so this is one way of correlating the structure to the rearrangements in our system. The second way is looking at the rearrangement probability. Okay, so once again, this is computed as a function of the order parameter or the softness in the system. So you see that smaller at the rearrangement probability increases with increase in softness. What it says is that softer the particle, larger is the probability that a particle with larger softness will rearrange. Okay, and this dependence diminishes as you go to lower densities. Okay, if you take suspensions that have lower densities, then this dependence on softness becomes very weak. Okay, so this once again, what it says is that if you go to higher densities, the correlation between the structure and then the rearrangements becomes stronger. Okay, so these are the kind of things that we can understand using our colloidal experiments. And this is just a visual impression of whatever is presented here. So we take a reference configuration, and for that we compute the softness or the structure order parameter, and that is the contour plots that you are seeing here. And then with respect to this configuration, we wait for for a time scale tau r. Okay, the tau r goes back to here. Okay, on this time scale, we look at rearrangements on this time scale with respect to a reference configuration, and identify the rearrangements in the system, and you see that most of them occur on these regions where the system is very soft or associated with higher structural order parameter. So I mean, what I've established is when you have rearrangements, what I've established is a strong correlation between structure and then the rearrangements under in quiescent systems, and the rearrangements here are occurring due to thermal fluctuations. So now what we want to do is we want to extend these ideas to sheared systems. Whether we can see similar kind of structure order correlation. So in sheared systems, what we are doing is once again we need to identify the rearrangements, and what I'm going to tell you is how do we identify the rearrangements. And this is based on the non-affine displacement of the particles. You have a particle, and then you have the neighbors. One can, by doing microscopy, one can compute the non-affine displacements the way. So this is the recipe, the recipe for computing the non-affine displacements is given in this particular paper by Falk and Langer. So essentially what you're doing is you're subtracting the affine component, which is the trivial component due to the applied shear, and then whatever is remaining is a non-affine component. Okay, so essentially if you have a displacements of this form, then this is affine. But then in disordered systems, most often what you have is you have deviations from affinity. So what we're computing is the deviation from affinity, and that is the non-affine displacement in our system. And based on this non-affine displacements, we're going to identify rearrangements. So once again, I showed you this movie in the beginning of the presentation, and what was plotted here is essentially the non-affine displacements in our system. So once again, what we do is we are shearing the system, and at different stages, we can compute the non-affine displacements around this is computed at a strain gamma, taking a strain window of delta gamma, or at around each gamma, we are taking a certain small strain window, or we are computing the non-affine displacements around that strain value. And this is delta gamma with respect to gamma, okay? And then we look at these non-affine displacements. Once again, we identify a time scale and then a length scale, not a time scale, the strain scale, okay? Here, strain scale and then the time scales are linearly dependent, so one can easily replace this with time scale. So we identify a strain scale based on the transition from subdiffusive to diffusive regime. So this is a point where we say it's going from subdiffusive to diffusive regime, because this is where the slope is becoming 1, okay? So we identify this strain scale, and we also identify the scale of the non-affine displacement. So if you have a particle, if you look at the particle motion over the strain scale, delta gamma r, and if a particle has a non-affine displacement greater than this, then we call that particle to be rearranged, okay? That particle has undergone rearrangement. That's how we identify rearrangements in our system. So the first thing that we did was we plotted the distribution of the structural order parameter as we strain the system, okay? So these are distributions of the softness of the structural order parameter at different strain values, starting from very low strain value to steady state, okay, 60%. You see that when you start start to deform the system, and then as you go to larger and larger strain, this is there is a slight shift to the right, which means that the average softness of the system, or the average structural order parameter, is increasing. So one can whatever information is there in this plot, one can look at the deviations from, we are not looking at S, the averages, but then we are looking at the deviations from averages, okay? Each plot is going to give us a certain average value of the structural order parameter. We look at the deviations, okay, with respect to gamma 0, which is the first frame, okay? So we look at the deviations of this change in softness or change in structural order parameter, and it is plotted as a function of gamma, okay, as you strain the system. And you see that what is happening is, as you strain the system, these are different strains. And after about 20%, there's a linear increase here. It appears to be linear, but we don't know what is the trend. But after a certain gamma, the system saturates, okay, which means that it enters a steady state. These are the yellow points, okay, that are these are the square, the black squares that correspond to the change in softness of the system, change in the order parameter of the system. And what is plotted on the right axis is the non-affine displacement as a function of gamma. Okay, so what we have done is, once again, we have done this kind of calculation. Okay, around each gamma, we have taken a window delta gamma, and then we have computed what is delta, the non-affine displacements, and we have taken the deviations. Whatever is done here, the same thing is done here. So you see that even the non-affine displacement show, the non-affine displacements characterize the dynamics in the system. Okay, just give me 2 minutes. I'll be done. So what we see here is that the non-affine displacements and then the structure order parameters seem to follow each other. Okay, so they yield and then saturate at the same point. What it says is that essentially there are the softness and then the non-affine displacements are correlated, or the plasticity in the system is correlated. So what I'll do is I'll just end my talk with this slide. What is shown here is we take a reference configuration, we compute once again the softness of the order parameter for the system, and that is what is the contour here. And then we strain the system with respect to that reference configuration, and we pick out only those particles where the rearrangements that are rearranging. Okay, these are the particles, the white dots are the particles that are rearranging. And as we progressively strain the system, we go to larger and larger strains. There are more and more particles that are rearranging or showing plastic behavior. And then they seem to pop up in this region where the order parameter or the softness is large, okay? And so essentially what we have established is that once again, even under shear, the rearrangements are determined by the structure, okay? So this is a movie, a small movie of what was shown in that those images, okay? So we can very nicely capture where these rearrangements are occurring. They are occurring in regions where the caging potential is shallower, okay, or the order parameter is larger. With that, I would like to thank you for your attention. And these are the conclusions. I would leave it and take questions from you.
We have time for a few.
These rearrangement zones that you see, so this would be, have you looked at the aging of this sample, and do these rearranging regions, do they, increase with...
Yeah, so there's essentially going back to Rajesh's work, I would say
using your softness potential.
We are looking at that. Yeah.
Okay.
We have not, done that so far.
Okay. Yeah. So can you, for instance, as you approach the the kinetically arrested state, can you think of a kind of a diverging length scale, like a static, like a dynamical correlation length?
Yeah, this is the first thing that we've looked at, and going forward, we will probably look at some of these questions.
Okay.
I'm not a glass expert, okay? I know how to shear glasses, but not really looking at those length scales. So, but for sure, that would be something interesting to look at.
Okay, thanks, Vijay.
So I had just one question that since you have these soft regions developing, percolating through your system, can I expect, or have you seen anything where fractures would appear perpendicular to those soft zones? Suppose you...
yeah, so we are looking at those aspects, the anisotropy aspects, even in these rearrangements.
If you were to expect fracture at some point of time or cracks, then I would expect that the non-soft regions would be the first to break under some sort of thing. And that could also be a pointer to your experimental pointer to where the soft zones are.
These are results this is like
to simulations, but
this is like a cake fresh out of the oven, okay? So we still have a lot of time to bake more cakes out of it. Yeah.